This will be topic corrosion at the quantum level, where Sudarsan and I will try to give you some insights into challenges we are facing in modeling, but also what we can learn. And corrosion is, of course, something everybody has met at some point in life. And it is a degradation of a material in an oxidizing environment we are living in. And I guess mostly we have seen things like this, and this is something we really do not want. And there has been also an estimate of what is the loss due to corrosion that was done by the National Association of Corrosion Engineers, and these are numbers for 2013, what I found, and it is like 2.5 trillion of US dollars, which is approximately 3.5% of the global gross domestic product, and these are really huge numbers. I think when we hear about corrosion, most of us think, okay, that's something we don't want and we really need to take care of it. But when I started working in this area, I actually found that there's an area where people would like to utilize corrosion, and I found this quite fascinating. For example, in medical applications, where people are looking at how to utilize the corrosion of magnesium and its alloys, since magnesium is a non-toxic material. So imagine you break something and then you have to have surgery so that they insert some nails and so on. But later on, rather than having a second surgery in order to remove this kind of insets, it would have been nice if they could simply corrode away. Unfortunately, also in this context, we face problems because the corrosion rate is not really controlled well. It's not controllable, and even this can lead also to poisoning if you have a too high concentration of hydrogen of the metals that evolve during the corrosion. The same way you can also poison yourself by simply drinking too much water. So in order to really deal with corrosion, we need to understand it. So if one looks at the Wikipedia, it says that corrosion is a natural process. Why? I mean, we're living in a metal-based society, and so we go to a great deal of trouble to extract metals from ores, for example, iron ores, in order to make steels. But when we think, we then also go to far away in order to try to protect them. So if I take a steel sheet, typically what is done as a first measure against corrosion protection is to apply a zinc coating, basically galvanize it. But of course, this is still a metal, and a metal in an oxidizing environment is not a thermodynamically ground state. The thermodynamic ground state would be some kind of oxidized form. So when the metal comes into contact with water, for example, then some kind of oxide, hydroxide, sulfide, or something, some oxidizing layer would form. And it would be nice if this layer is really protective, and there are oxide layers that are protective and really prevent further corrosion of the material, but this is not always the case. So in order to understand when a layer is protective, when it is not, how does it come into being, and what are the processes that govern it, we really need to understand corrosion. And not only at the macroscopic level where we observe it, but really try to go to the microscopic level. And I'll try to convince you that why we need the macroscopic understanding. Afterwards, I would like to address challenges that we are facing in ab initio modeling of corrosion processes, and show you how addressing these challenges also allows us to learn about the different processes and the importance of, let's say, water or reactions or different things that we observe. Then I'll hand over to Sudarsan, who will show you an example of how we have of some method development which allowed us to address a question of anomalous hydrogen evolution on magnesium. So basically hydrogen evolving on a positively charged magnesium, which is something which is completely counterintuitive, so since this reaction consumes electrons. And then we'll come to the end, hopefully on time. And so why do we need to understand the microscopic scale if actually we observe and see this failure of materials at the macroscopic scale. When you zoom in closer to the interface, when it comes, you will start seeing atomistic details. And what we know that usually if water, let's say, comes into contact with a metal, they have different surface dipoles, and so there will be a potential drop. This will be also enhanced by the presence of ions that are solvated in the aqueous environment. And what is built up is something that is called the double layer. This is basically the change of this potential as it approaches the bulk value. And what is interesting for us is that this potential drop is really very big, close to the interface within this Helmholtz layer. And this is, you know, you have a surface, an interface, which is in a field, and obviously the presence of this field will influence the reactions that are going on. It may lower barriers or may enhance them. And so if, in order to really start having a national design of materials in order to improve their corrosion properties and control them, we need to understand the processes that are going on at such interfaces. And this is what we'll be focusing on. So if I zoom into this interface, I see that there are ions with their solvated shells, solvation shells of water around them. But also there are the surface, I don't have just the metal, but I may have kind of oxides that form. I may have adsorbed ions. I may have reactions that occur, and a lot of things are going on. And at the microscopic level, what we are interested in and what occurs there is the making and breaking of bonds, which is essential to any kind of reaction or chemical process. And so we need to understand this look at the making and breaking of bonds in order to understand the chemical reactions, which leads to the occurrence of such oxide films or generally the degradation of the materials. So what are the things that we are generally interested in when looking at such nanoscopic level? Of course, we would like to know about the structure, because this is essential, you know, whether an ion would go in this direction, whether two atoms can adsorb somewhere and then react or not. And the structural information is manifold. So defects are usually interesting because these are imperfections in the material which are usually prone to attack. We have heard in the talks by Stefan Sefferer and also by Baptiste Gold how they are trying to understand the structure of basically the bulk, looking at grain boundaries or line defects and how they are interacting with the environment or how they change. In context of, let's say, growth of oxide films, also point defects have been considered to be important because they are channels for growth of the oxide. In this talk, we will be particularly interested in the interfaces between the solid and the liquid, and so this is what I will be focusing on. But when we are talking about interfaces, we need also to understand what kind of surface orientation we have. Maybe the surface changes under the influence of the environment, so there are reconstructions and so on. Essential in this context is also the electronic structure, because this is something that will influence the chemical reactions. And we also need to understand energetics, which relates, for example, to barriers, or how easy it is to take an atom out of the metal and dissolving in the solution. And for all of these quantities or processes, we need to understand how they're influenced by the environment, which is, as I showed in the previous slide, influenced by the double layer, which basically means we need to know how pH, electrode potential, temperature influence the processes we are studying. Of course, we are not only addressing this point from theory, also experimentalists try to address it, and they are using techniques. So I'm not talking about the conventional electrochemical techniques, but rather experimental techniques, which allow us to address the obtain nanoscopic information. And such techniques are usually coming from the realm of surface science, where they have been successfully used for years, also where the Turing experiments are working complementary to each other. But the presence of an aqueous environment makes it also challenging to apply these techniques to studying such solid-liquid interfaces. And there are topographic or image resolution techniques such as scanning electron microscopy or spectroscopy or atom force microscopy. And there are beautiful works, for example, in the group of Philippe AQUEOUS, where they're looking really at passive film at surfaces and trying to understand what makes the film passive and how does the interface look like. Then there are techniques which allow us to resolve the chemical states, such as X-rays, photoelectron spectroscopy. And if this is carried out at the synchrotron, for example, and in order to get really high resolution, we can also get information about a local coordination and compare also to theory. Then optical techniques are very promising, and there are a range of techniques that are used. Here is an example from work of Andreas Erbe, who has looked at the germanium water interface and really looked at the transition or a state that evolves at the surface as a function of the change of the potential. And in corrosion, a technique that is still also used, though it is more an ex situ technique in the context of the solid-liquid interface, is TOF-SIMS in order to get information about the depth or also a mass resolution. Now, the same questions the same interface we are also would like to address with density functional theory, and hopefully get information that is maybe not accessible to experiment and eventually achieve the same kind of synergy effects that we have in the realm of surface science. So the question is, can we use density functional theory to study and analyze and even quantify the processes? For example, a dissolution process, so how an atom leaves the metal surface and turns eventually into an ion, which is something we perceive as being the most fundamental step in a corrosion process. Now, I should mention before going on that actually at this nanoscopic scale, the processes or the mechanisms we are looking at, be it in the context of corrosion or even battery materials, water splitting, electrocatalysis, are very similar. So when we learn something about this interface, it would be also applicable to other fields. Now, I would like to address a little bit the challenges that we are facing in ab initio modeling and how we were kind of trying to overcome them in order to learn something about the material. So the very first challenge any kind of atomistic modeling technique is facing is structural complexity, because I've drawn here kind of the metal in a very schematic way, but where this has line defects, which are, if one would like to model a grain boundary, we have to go into see how do we describe this. Obviously, I can't describe this whole interface in a DFT calculation, that given that our cells usually contain a few hundred atoms. And so we have to consider that we have different materials classes, but also to translate this complexity into representative atomic structure. How do we go about it? If we would like, of course, to learn something about the ions in solution, we would have to kind of cut up out of this system a part that would allow us to study the properties of this ion. If we are more interested in learning something about the growth of the oxide and the role of point defects within this growth, then we will focus on part of the oxide. So basically only look at this part. But again, I said I would like to look at the solid liquid interface. So I will kind of ignore these bulk parts where we can work on. The different materials classes I mentioned. So if we consider the electronic structure, for example, an oxide is, of course, from an electronic structure point of view, very different from metal, since it does have a band gap, so an area which is forbidden for electrons, though we don't have states. We also have to consider from the point of the structure that water is something that is not, doesn't have a fixed form like a metal or an oxide, so it doesn't have a lattice, but it's more like an amorphous material, and we need to take this into account. So let me first talk about how do we deal with really modeling the aqueous environment. We could take the surface science approach and basically just consider a surface in contact with one or a few water layers. And this has been done for a long time, and the studies were mostly addressing metals. We have learned a lot of these studies, but of course they are limiting, and we are starting also to learn about the limitations that we are facing in such a kind of setup. So the next kind of more complicated things we can do in order to really simulate not only a few water layers at the surface, but consider that this surface, these few water layers are attached to a continuum of bulk water, is to use an implicit solvent. Basically, we consider that within this region, which is here shown as a vacuum, so white, we have the electric continuum with screens and has the screening properties of water. It can polarize and in this way account for changes of the interfaces. This is attractive because it is computationally very efficient. There is not much overhead in terms of computational time that we need to invest compared to this kind of surface science calculations. And so it allows us to get first information as to how much effects of bulk water are important, for example, regarding the stability of surfaces. This is a question we asked ourselves. So do we have to consider the bulk of water in order to understand what kind of surface structures may form? And the material we looked at was zinc oxide, and we looked at the polar surface. So what you see here, for those of you who are not used so much to looking at atomic structure, so here in gray we have the zinc atoms, in red we have oxygen atoms, and they are of course bound within a Wurtzite structure, which makes up the structure of zinc oxide. And the polar orientation means simply that along a polar orientation we have at the surface only one kind of atom which are terminating it. So in order to understand what is the impact of the solvent, we performed calculations without a solvent. So basically the usual surface science kind of setup in which we have our substrate, we have a vacuum region, and we can consider different structures at this surface involving water or water fragments. And then we considered the same structures and simply added an implicit solvent in order to be able to account for the changes due to the environment. What we calculated were Pourbaix diagrams. So for those of you not familiar with Pourbaix diagrams, these are thermodynamics diagrams which show what are stable phases under different conditions. And the different conditions in an electrochemical environment will be the pH value and the electrode potential with respect to some reference, which is in electrochemistry, typically the standard hydrogen electrode. So there are a lot of details there. I don't want you to focus on this. Just know that there are regions of different colors. And each of these regions of different colors corresponds to a different surface structure. And I have shown some of these surface structures here. So these two structures are one where we simply have the flat surface, but different water derivative adsorbates. So in this case, these were OH groups, which were at the surface in different coverages. Here within this region, we have a somewhat more complicated reconstruction in where part of the surface atoms are missing and it is forming such a triangular pit within the surface. If you look at these two Pourbaix diagrams, one for the calculation without a solvent and one with the solvent, just looking at the different colors, you will see that things are changing. And we are having different structures that seem to be stabilized depending on whether we consider the solvent or not. And what is striking is that in the Courbet diagram where we consider the solvent, we have a lot of this kind of triangular reconstruction that appear at the surface. Now, what is the correct one? Fortunately, we do have some experimental evidence of what we should expect. So this is an AFM image that was taken in the group of Marcus Volkina. And the conditions under which this was taken is marked here by the yellow dot. What you can see that here we do see definitely such triangular reconstruction, which implicates that the diagram we have calculated in the presence of the solvent is representing what is also observed in experiment. So we need really the solvent. I don't have time to go into too many details, you know, why we need the solvent. We investigated this in great detail, but what we found, the conclusions, is that dissolution effects can be really substantial and can change this, what we observe in the structures. They're also very selective and favor reconstructions which have unfavorable electrostatic interactions in vacuum, because the solvent can effectively screen these interactions. Of course, the best thing we could do is to really use an explicit solvent, so basically consider real water molecule, and this is the most realistic and most flexible description of this solid-liquid interface we can consider. However, it is also the one which is computationally most intense. Why? Because, of course, the water structure is not rigid, and we need to consider all these fluctuations and changes that are occurring there, and we need to use for this ab initio molecular dynamic simulations. This phase where it would allow us to access also free energies, but one of the problems that we are facing is, for example, the time scale. So 100 picoseconds trajectory is actually a very long trajectory for an MD simulation, but in terms of what is seen or used in experiment, it is not very long. Still, as Sudarsan will show you, we even with the shorter trajectories we can still learn a lot about mechanisms. When we go to an explicit water, one thing we have to consider is also the electronic structure. So in the implicit solvent, or even when we consider just a few layers, we don't really care so much about the band structure or the electronic structure of the water, or we can't access it. But water has a band gap, and experimentally this is measured to be in the order of 10 eV. Now, density functional theory, while being an exact theory, in the flavor of Concham, which all of we are using, of course, lumps all many body effects into something that is called the exchange correlation potential. And to this, we have only approximations. And it is a well-known fact that our standard functional, semi-local functionals actually underestimate band gaps. So what is shown here is basically the energy with respect to the vacuum level, which is an absolute reference, and we show the conduction band and minimum and the valence band maximum, so basically the band gap for the experimental water experiment measured, and also for different functionals. And you can see that we can actually describe the water band gap quite well. However, the functional that is used here is extremely expensive. So this is a hybrid functional, and while we use it for benchmark calculation, it is not something that at the current stage we can use for a production run. So what are the consequences? Of course, we need always to be very critical of our simulations, but let's imagine in the context of corrosion or any kind of process what may happen. If we describe, if we have here a metal, we have here a semiconductor, and we have here some redox level for a reaction. Now, if the valence band maximum is above this reaction level, then we may have a electron transfer, and this reaction may actually occur. But if we have this situation, then an electron exchange may not occur, and this reaction may not happen. So depending on how well we describe our also electronic structure, we may find some effect or not. And therefore, we need to be really careful of what we are doing. And these are questions before really starting to address the effect of the environment. So the Bourbet diagram, which I showed you, basically relied on combining density functional theory with thermodynamic modeling, and the effect of the electrode potential and the pH were kind of considered a posteriori, so in an implicit manner. But of course, if we have explicit fields which are present in these calculations, they may also have an influence. And so I will now hand over to Sudarsan, who will tell you how we can attain potential control in our calculations, and then look at a very interesting example of magnesium corrosion. Okay, Sudarsan, your turn.
And if you can't, just let me know. So thank you, Mira, for the nice introduction into the topic of ab initio and atomistic modeling of corrosion processes. So in this part of the talk, that is my part of the talk, I'll be talking about two things that we've done in our group. The first thing is the development of a potentiostat can actually use to perform ab initio DFT calculations of these interfaces under the influence of an applied. And the second part of this talk, I'll be showing you an example where we use such said potentiostat to study corrosion processes, specifically hydrogen evolution on magnesium. Now, in order to motivate this portion of the talk a little bit, we need to know what potential control in an electrochemical setup actually means. Right. So in order to understand that, consider an electrolytic cell with an anode and a cathode, which is maintained at a potential difference U. Let's say you have a certain electrolyte within an aqueous electrolyte within the two electrodes. If there is a dissociation event, let's say where a water molecule splits into a H plus and an OH minus ion, what would happen initially, because of the potential difference, is that the ions would migrate to the electrodes, the anode to the anion to the anode, and the cation to the cathode. What happens as a result of this migration is that there will be a certain amount of screening by these ions. So what would happen is, if the initial potential that was maintained by the potentiostat was U, because of the screening, this would be reduced by an amount of delta U. So what would a potentiostat, whose job is to maintain this given potential, do? Is that it will supply current, or in other words, charge to the electrodes. So you now have additional charge on both the anode and the cathode, and now you've retained your original potential U. This is what a potentiostat does in reality. If you look carefully at the individual electrodes, the total number of electrons and the total number of ions at these electrodes have changed during such a process. In terms of thermodynamics, what this means is that these individual half-cell electrodes are grand canonical, or thermodynamically open with respect to electrons as well as ions in the system. However, if you look at the system as a whole, the total number of electrons and the total number of atoms in the system, which means the setup as a whole is canonical. So the question we have to ask ourselves is, yes, this is something that experimentalists can do quite easily, applying a potential bias in the electrochemical setups, but can we actually do this in standard density functional theory calculation? Well, the answer is that it's very challenging. Why is it challenging? Well, there are two reasons. The first reason is something known as periodic boundary conditions. So usually in most of the density functional theory, we simulate atomic structures in what's known as a supercell, which means that you have periodic boundary conditions on all three directions. In order to create surfaces, what is typically done is you take a crystal and then you cut the crystal along a certain orientation which you would like, and you introduce artificial periodicity by adding a vacuum or something like that. So what in this structure we see how we create a metal surface. Naturally, because of periodic boundary conditions, you see that you can actually see its periodic image along the surface direction. Now, in order to apply a potential bias between the two electrodes, you will have to apply a potential that looks something like this. However, a certain limitation is that because of periodic boundary conditions, this point and this point, this boundary, the atoms at this boundary, and the corresponding potential should be equal. In other words, the potentials at these 2 points should be exactly the same, and there shouldn't be any sort of discontinuity in the potential. This is one challenge in applying electric bias at for these calculations. The second condition is the condition of a single global Fermi level in these DFT calculations. So what does this mean? In order to maintain two different metals at two different potentials and have a bias between them, what you would have to do is essentially have them maintain at two different Fermi levels, as shown in this diagram. Metal A and metal B at two different Fermi levels. However, density functional theory is a ground state, always tries to get the electronic ground state. And as a consequence of obtaining this ground state, you can only have a single global Fermi level throughout the supercell. It means that even if you start with a situation like this, at the end of a DFT calculation, you would end up in a situation where both the metals would have the same Fermi level, and therefore you can't really have an electric field between two metals. This has been one of the biggest challenges in density functional theory modeling of such interfaces. So the solution that we came up with to overcome this problem is to think, hey, why don't we actually use a semiconductor as one of the electrodes and use in order to model the phenomena that happens at the working electrode. And therefore you would have a situation which looks like this. So we just replace one of the electrodes with a semiconductor, a computational semiconductor. A semiconductor has a band gap, which we assume would straddle the Fermi level of the metal. What we then do is introduce some kind of doping. It could be either p-type doping, where we take away electrons from the valence band of the semiconductor, or alternatively, it could be n-type doping, where we band of the semiconductor. What happens now is that because you have empty states below the Fermi level of the metal, there will be a spontaneous transfer of electrons from the Fermi level of the metal in order to occupy the states in the semiconductor. As a result of this, you would have a positive charge on the metal and a negative charge on the semiconductor, and therefore by Gauss's law, you would have an electric field between the two electrodes and therefore a potential difference. So this is the fundamental idea of ours. Of course, this sounds good in theory, but how do we actually do this in practice? And in order to do this in practice, the first thing that we have to find is a suitable semiconductor which can actually realize this setup. We are interested in the simulation of metal-water interfaces. So, in order to simulate these interfaces accurately, we have to also take into account the fact that the solvents, which is usually water, also has. That means a semiconductor should have a band gap or should have its band edges such as it straddles both the Fermi level of the metal and the band edges of whichever solvent you're about. In other words, you need a semiconductor with a really, really large band gap. So we simply Google which is the material which has the largest band gap. Surprisingly, the answer to this is neon, which seems a little bit bizarre for electrochemists. However, neon is indeed the crystal with the largest band gap known in nature. Experimentally, this band gap is about 22 electron volts, but even with density functional theory with semi-local functions, which is infamously known to reduce the band gaps, it still has a band gap of about 11.48 electrons, which is actually quite huge. The nice thing about neon is that these neon atoms are closed-shelled atoms, and they only have weak van der Waals interactions between them, which means you can strain it to match any lattice dimension. So how do we construct the supercell in us? This is quite similar to the setup that I showed earlier, except that instead of having a metal counter electrode, we have a layer of the semiconductor counter electrode and the metal working electrode. In order to charge the neon electrodes, we use the concept of pseudoatoms. By pseudoatoms, what we mean is we change the valence as well as the core charge of the electrons in order to induce the doping that I mentioned earlier, and therefore create the field between the two electrons. Of course, because we change the core as well as the valence charge, we can actually maintain charge neutrality, which is a necessity for DFT calculations. However, we still have periodic boundary conditions, which means that we still have to take care of the fact that the potential at this point and this point should be exactly the same. In order to take care of this artificial potential field, this field that is generated between the two surfaces, we apply what's known as a dipole correction, where we place a sheet of artificial charge dipole in this vacuum region in order to get rid of this field in the vacuum region, and I have two well-defined vacuum levels, potential levels in vacuum. In this region between the two electrodes, this valve will then place the electrolyte in order. Now, I've described how we set up a typical atomic structure to perform calculations where we apply a field. Now, how do we actually do a potentiostat? Well, the workflow for a potentiostat is shown as given over here. I will not go much into the details, but in a nutshell, what we do is we perform molecular dynamics and monitor the potential drop at every given snapshot in a molecular dynamics simulations. And based on what the target voltage is, we either increase the charge or decrease it based on a sort of mixing algorithm. And as a consequence of this mixing algorithm, we would be able to maintain a given average potential for a trajectory. This is an example of how the fluctuations in the potential would look like in a typical potential controlled molecular dynamics simulations. You can see the blue instantaneous value of the work function fluctuates due to the dynamics of the system. However, the average potential drop is maintained by the potentiostat. This is what a computational potentiostat would do. Right. So we now have a potentiostat which actually helps us do these simulations. Now we would like to use this to study an application that is very important to us. And we choose the study of magnesium corrosion. So why is magnesium corrosion so important? The reason is quite straightforward. So magnesium and its alloys are very promising for engineering, battery, as well as biomedical applications. And one of the reasons why it's so attractive is it's because it's about 4 times as lighter as steel. It's even lighter than aluminum, which means that if you use it for engineering applications, you can make your appliances a lot more energy efficient. However, a major problem with magnesium is that it has a very low corrosion resistance, especially to aqueous corrosion, which can be seen in the galvanic series of different engineering elements and alloys. It is easily the most corrosive of all engineering metals. What's very peculiar about corrosion of magnesium is that not only do you see metal corrosion in these on magnesium when you polarize it anodically, you also see the evolution of hydrogen from magnesium under anodic conditions. That's what you can see in this movie, where you see hydrogen bubbles coming out of a magnesium surface in an aqueous. This is quite puzzling, and this is known as anomalous hydrogen evolution, because hydrogen evolution is an electron-consuming reaction, like Mira has mentioned earlier. However, this happens under anodic conditions where there is a deficiency of electrons in the metal. So this phenomenon, which has been known found out way back in 1866, has puzzled the community for a lot of years. Atomistic mechanisms of how this reaction actually happens is not very clear. So our idea is that since we have this new ab initio potentiostat, can we actually use this to study such mechanisms and to understand what goes on? In order to do this, we actually take the setup that I described earlier. We take a 3x4 layer of a magnesium 001 closed pack surface, and we place a certain layer of water molecules on top of it, and then confine it with the neon electrode, as mentioned earlier, in order to apply. And then we perform our DFT-MD calculations to see what's going on. So what I'm about to show you is the results from our density functional theory molecular dynamics calculations, where we track the trajectories of the ions in our simulation. So what we do is we don't track the trajectories of the water molecules that are intact, but only those of the ions that are there. So what happens very quickly is that you see a water dissociation reaction on the surface of the magnesium. Right? So that's indicated. The presence of the OH that is adsorbed on the surface is indicated by the red line over here, and the hydrogen that is adsorbed on the surface is much more mobile, as you can see in the movie, and it's able to occupy surface as well as subsurface sites in the magnesium. This is what you observe under open circuit conditions where you don't apply any sort of field. What we do is we repeat the very same calculation, but we now apply potential control and make the magnesium more positive charge. In other words, we apply anodic conditions to the system. And we do the same thing. We again track the trajectories of the what we see now is something that is much more colorful. First of all, we do see the water dissociation and absorption, which we also saw for the case of the open circuit conditions. We see that the hydroxyl layer, the OH layer, does not stop at 1/3 of a monolayer, but that it goes to a complete monolayer coverage on the surface of the magnesium. Of course, the hydrogen once again is able to penetrate the magnesium. We also see two other things. First, we see the proton transfer from the surface of the magnesium to the counter electrode. But this happens due to a Grote's mechanism and the applied electric field. So hydronium ion that is formed in solution would like to migrate to the negatively charged neon electrode. More excitingly for us, what we also see from these simulations, from these violet, or let's say violet curves, is the evolution of hydrogen from the surface of the magnesium. This is really what we wanted to see during these simulations. So the advantage of such DFT-MD calculations is that we could actually go to the very snapshots where these reactions happen and see how the atoms move, and to understand the mechanism of such a reaction. So we take into account one such reaction that happens at about 6.4 picoseconds, and we just look at what happens at the surface. Here you can see the surface of magnesium, where we have a certain coverage of OH ions adsorbed on the surface and a single hydrogen adsorbate which is on the surface. What we see is that a water molecule approaches the surface, and one of the oxygen-hydrogen bonds is pointing in such a way that it points towards the adsorbate hydrogen. What happens then is that this OH bond, this hydrogen from the water, is actually able to attach itself to the adsorbed hydrogen. And what happens later on is that the OH bond is broken, and then you get OH in solution and the evolution of hydrogen. And this is the mechanism of the hydrogen evolution. However, something that was very puzzling is this certain configuration. Because you expect the hydrogen that is attached to a water molecule to have a slightly positive charge, which means the only way that such a bond can be established electrostatically is if this hydrogen that is adsorbed on the surface is negatively charged. And this is exactly what we find from a charge density analysis scheme. We actually find that when hydrogen is adsorbed on magnesium, due to the polarizability of the magnesium electrons, the adsorbate is not neutral nor positively charged, but it is actually negatively charged. This negatively charged adsorbate reacts with water to give us hydrogen molecule and an OH minus, which eventually adsorbs on. So this is the mechanism that we found out from our DFT calculations using the potentiostat. And the nice thing about this is a really novel mechanism that could explain why this happens under anodic conditions, because cathodic conditions, that's electron-rich conditions, are not necessary. In other words, the electron does not come from the potentiostat, but rather from the adsorbate, the hydrogen. So this is one application where we use such a potentiostat. The second application is to study the mechanism of metal dissolution, which is essentially the very first step of metal corrosion. In order to simulate this, we created what's known as a vicinal surface, not a clean, ideal 11001 surface, but rather a vicinal surfaces which has step atoms and kink atoms. These kink atoms that you see here that are highlighted in silver are usually atoms of the metal that have a lower coordination. It means that we expect them to be much more susceptible to dissolution. And what I'm about to show you is a movie of the dissolution processes that we generated from our molecular dynamics simulations under the influence of an anodic. This is what we see here. If you look at this kink atom of the magnesium, you see how the water molecules are able to surround them, and eventually is able to break its bond with other magnesium atoms, and eventually is able to dissolve as an ion in solution. This is the this is true to its name, is a quantum mechanics-based simulation of how the fundamental corrosion process occurs. I'm about to show you the same movie once more, but what I've done now, I've removed all the molecules that actually don't participate in the dissolution process. So just to give a clear picture of what actually goes on. What you can actually see is even before the dissolution reaction starts, you have an OH ion that is adsorbed on the surface of the, on the king site, on the surface of the magnesium. What this OH adsorption does is that it makes the king site actually slightly positively charged. And once the, I can probably play the movie here. And so once the dissolution process starts, what happens is that this king site is already a little bit ionic. And once the potential is applied, it's able to break its bond and then form a solvation shell with the water molecules surrounding it. And so this is basically how the dissolution, the beginning of the very fundamental step of the dissolution process in magnesium occurs. And all this has been done using the potentiostat scheme, which allows us to accelerate such reactions. So in conclusion of my portion of the talk, I've showed you basically how we've developed and implemented a fully ab initio potentiostat scheme, which can be used with any density functional theory code with periodic boundary conditions. Using such a potentiostat, I hope I've been able to demonstrate how we identify a novel reaction mechanism for the hydrogen evolution on magnesium under anodic conditions. And finally, we use it to identify the initial steps of magnesium corrosion in an aqueous environment. With this, I'd like to stop my portion of the talk, and I'd like to hand it back to Mira, who would probably conclude this entire session.
Yeah, so thank you very much, Sudarsan. So I would just like to give a general conclusion. I hope we were able to convince you that using density functional theory and really pushing the boundaries of what we are able to do allows us to get valuable insights. And of course, we can use one of the advantages the theory always have, that we can switch on artificially certain contributions or switch them on and really see the effect that they have on certain processes or reactions. And this, of course, opens the way to, get a microscopic understanding of processes at the nanoscopic scale, which are hopefully going to benefit also the rational design of corrosion protection strategies.